Yesterday we did the f of g and the g of f here, but you need to look at the composition where you're doing f of f and g of g. And basically what it means is we're going to take a function, and wherever we see an x, we're going to replace that x with the exact same function. So we had started by talking domain with these because you have to think about domain all the way through the problem, from the very beginning to the end. And we said 3 is a no-go on this one. So negative infinity to 3, union 3 to infinity. Basically, if you think number line, you'd have to hop over the 3. You know, everything else is good. You're coming in from the left, hop over the 3, and take off. But this one, because we want to be able to take the square root, we're going to have to restrict that domain. And 0 is okay for square root, because the square root of 0 is 0. But we can't do the negatives in there, otherwise we'll be in imaginary land, and that's not what this is about. This is application math in pre-calculus, so we don't encounter the square root of negatives very often. So our composition started off with f of g and g of f and seeing what happens to the domain as we work those two together. And we have to do that again. So we start by knowing, hey, there are restrictions in this domain, but we watch as we take each step what happens to the domain. So I'm going to rewrite f of x right there. And since it's f of x, what we have to do is replace this little x right here with 1 over x minus 3 again. So it'll be 1 over x minus 3 minus 3. Oh, we've done that stuff. This is a complex fraction. We have a fraction within a fraction. So what we generally do is we slap a 1 under there and say, okay, if I'm going to do that subtraction, I am going to need a common denominator for this bottom piece here, and that would be x minus 3. Now we could also multiply everything in this equation by the LCD. That was another method that we have, but most people remember this one before the other. So this will now give me, because x minus 3 will be my denominator, down here, I have 1, and then it'll be minus 3x. I'm going to have to make that bigger. You're not going to be able to see that towards the back. Plus 9 over x minus 3, and now I'm going to start to use parentheses so I don't lose track of anything. And that will be 1 over, well, 1 plus 9 is 10, so negative 3x plus 10 over x minus 3. And then we realize, wait a minute, when you have 1 over something, that's just the reciprocal, because we have to flip that over and multiply. So this is really x minus 3 over negative 3x plus 10. So that's what we get for f of f. Now, we want to go back and say to ourselves, is there a way here to talk about that domain? Has it changed as we went through there? Well, right here, our denominator was still x minus 3. So,
okay, wait, what? Hold on. What's weird? The stuff you just did going before that. How did you just flip like 3 different things?
right here, we're taking 1 and we're going to divide it by this mess. But in order to see this as one fraction, we have to get a common denominator. That's the only way we can put that together. So what we do is we multiply the top and the bottom here by that x minus 3 so we can get that common denominator. And then it would actually look like this. And we could go ahead and put these together because it has a common denominator. You're right, I skipped a step. I probably shouldn't have done that. And then we go ahead and simplify that and we see, wait a minute, if it's 1 over the top, that'd be like 1 over 1 times x minus 3 over negative 3x plus 10. And that's just the reciprocal. So that's how we get reciprocals, is basically you take 1 and divide it by a fraction. All right, so now we've got this. And we remember, okay, domain was already restricted, couldn't use 3. But as we get closer and closer here, we notice, okay, wait a minute now. We're going to have a new denominator down here. And that means there's going to be a new restriction on the denominator, because now not only can I not use 3 because that was a restriction before, but whatever makes this denominator equal to 0 is also a problem.
Why did you flip it there?
Because it was 1 divided by this. So what we would do, since we don't divide fractions, is we would multiply by the reciprocal. See, I was crunched for space. I should have just, I'm going to move this down right now so I don't skip any steps with the next one and get anybody confused about that. All right. So when we take 1 and divide it by something, that gives us the reciprocal. And that's what we ended up with here. So now we know we can't use 3, so I'm kind of keeping that in the back of my mind. X can't be 3. But here, if negative 3x plus 10 equals 0, then we also have a problem. So we're going to have to subtract the 10 from both sides. And then we're going to have to go ahead and divide by negative 3. Again, in the back of our mind, x can't be 3, and now we know it can't be 10/3. So easiest to think number 1. All right, we're coming in from negative infinity. And we're going to hit a problem spot. Which problem spot are we going to hit first, 3 or 10/3? Going to hit the 3 first, so that's a problem. Got to jump over that, start in again. Going to hit the next problem spot, which is where? 10/3. And then we're going to have to jump over that, and we can go on. So again, easiest with domain, think number line. You're over here at the negatives as you work your way over. What can you use? What can't you use? So that one got pretty involved there for the domain. This one is g of g. And g was g of x equals the square root of x. So a restriction on the domain already. 0 to infinity. Thinking about that as we work through the problem. So if I'm going to do g of x, that means I have to take this and I have to put it in there. Wait a minute, that'll be the square root of a square root. It is. You've got a double root taking place here. But you know what? Often with a double root, if you don't think of it as a radical and you start thinking in terms of fraction powers, you can usually simplify it a little bit. So what we really have here is x to the 1/2, and it's being raised to the 1/2 power. Because square root is 1/2 power. You guys remember all that, right? Square root's 1/2 power, cube root's 1/3 power. Okay. So now we have powers, and we have all kinds of rules for exponents. And we think, okay, when you raise a power to a power, you multiply. 1/2 times 1/2, top times top, bottom times bottom. And we get that, which is a lot simpler. But the problem did come to us with roots, with radicals. So now that we know what that is, now we put it back in radical form, and that will be the 4th root of x. So while I was going through this, I think, okay, my domain was 0 on up, and that was because I had an even root. And I'm looking through this, and I'm looking for any division, because that's when I would need to add something to that domain restriction, and I don't see it. We end with an even root, and that's what we started with. So the domain is going to be exactly the same as it was when it was square root. And that's going to be 0 to infinity. So 2 things you watch for as you're doing the compositions. Am I suddenly out of nowhere having to take an even root? Because if I am, then I better figure out what numbers I can use for that even root. And is there division in this process? Because if there is, I have to watch out and make sure that I'm not going to divide by 0. So those are the new things that can happen as you work through those composition problems. All right, those were a little involved, but now I thought this next piece you're going to like this, because it's one of those things where it's generally not the most complicated thing, but if people are prone to overthinking, then you might struggle a little bit with it. So here's what I want you to do. Just kind of go, come on. Oh, come on. Get the brain to empty out. All right, well then a deep breath. Don't overthink. That's the danger with this, decomposition. When we do stuff in calculus, there are times when the problem can't be integrated or differentiated because there's too much going on. So what we do is we pick it apart into pieces. And so what we're doing here when we're decomposing these functions is to get ourselves in a situation where we're working with two easier things instead of some monster problem to start with. Because when we compose them and put them together, they give us this. So we want to know what are the easier things to work with when we get there. So like it says, be aware, there's often more than one way to decompose a function. If you are doing your homework and you're thinking this was the easiest way and you've got an answer and you look in the back and it's not your answer, I wouldn't worry too much because there are a lot of ways to do this. So this one says for each of our functions h of x, let me see here, find functions f and g such that when you compose them in this order, remember order is important, f of g of x, you would get this. So I look at this and I think, okay, I'm going to start with f of x. This is what I would want to substitute into. But I also start thinking, what would be something easy to substitute into it? And I see these nice parentheses with the x plus 1 in there. And I think that's kind of built for, hey, shove this in its place. So I'm going to make g of x equal to x plus 1. So once I've done that, I'm saying this is what I want to put into the other one. What do we replace? When we do composition, what do we replace? X. Think about that for a second. You see how if we just took our x plus 1 and we put it in for x in both of those positions, it would say exactly what we see in h of x. So there's two things to think about. What's the one I'm going to use for the substitution and what am I going to substitute? Those are the two things. And like I said, there's more than one way to do this. So the important thing is the f is what we're going to substitute into. So we think about what we have here. And then we say to ourselves, self, I could replace that x with what? Lots of ways to do this one. What could you pull out of that and then put it back in? Okay. Sounds great. So I looked at that and said, I'm going to take the whole thing. Does it work? Okay, Cassie, you're shaking your head. That's not what you did, was it? What'd you do? What did you do? Oh, you factored this out. What you're doing is looking for solutions. And we're not solving this. We just want to make an f of g situation work. Emmy.
You just take out the x to the third, back to the g, and then that's
That work? More than one way. You know, more than one way. So this is decomposition. It's all about decisions. You have to make your decision about what's going to be the original and then what are you going to substitute in. So now, why do we do that? Because unfortunately, there's not this giant book of formulas somewhere for every situation that you ever encounter. And what we have to do is come up with calculations, well, in this case, calculations that save people's lives. When that happens, you need to figure out, okay, how can I use the background information that I know to get what I need? So this one says in the medical procedure known as angioplasty, doctors insert a catheter into a heart vein through a large peripheral vein and they inflate a small spherical balloon on the tip of the catheter. Suppose the balloon is inflated at a constant rate of 44 cubic millimeters per second. You might have had grandparents it's done before. But it literally is what they do, and it's very non-invasive. You know, it's a little teeny hole somewhere, generally down in the leg to get through the arteries, and then they feed their little tube up through it, and they find where the artery is clogged. They blow up the balloon a little bit, and it pushes the plaque that's been inside those veins and arteries back. And then they put what's called a stent in there. And it's just a little piece of wire that they can pull to make stay in position and keep that open. So it's really important. I mean, you certainly can't have your balloon just keep filling and keep filling and keep filling when you've got somebody on the table and you have this happening. You have to know how far should we go with this. So these balloons are attached to this tube, and there's a machine at the end that is filling this 44 cubic millimeters per second. Now, why is that important? Because if we want to know how much air to put into that balloon, we're going to have to tell them how many seconds we should run that thing. Because we know each second is 44 cubic millimeters. So if you need 88, 2 seconds, boom, it's off. And you've got it. So this is find the volume after t seconds. And we think, wait a minute though, this is a sphere. Anybody remember the volume of a sphere formula? So who wants to be a millionaire question? Too long ago? 4/3 pi r cubed. So question for you. You see a T in there. There's no T. So if we're supposed to find the volume after t seconds, we're going to have to figure out how to replace that R value in here with something that would make sense for that. So the first thing we'd want to do is say, all right, pretty obviously we can't use R. So let's see what we can get if we solve this for R. So volume equals 4/3 pi r cubed, and we're going to get the radius all by itself. So what would you do first to get the radius along? And we probably just write that as 3v over 4. Then what do you do? Divide by pi. Then what do you do? Cubed root. That looks scary. But what we just did here was we figured out a way to find the radius of that balloon using our volume formula. And that's important because this is about volume. I mean, we've got cubic millimeters there. That is volume. So now we think, okay, how do I put all of that information together? So it says when the volume is V, what is the radius R? That's what we just found. And then it says, what would R of V be? You know, how do we put all that together? That's the piece we're finding as well. Oh, actually, this one was just R. I've got ahead of myself way up there. Here's where they wanted us to just leave R as the variable. The second one is where we had T. I got ahead of it. So I go back to my V of T, and I realize that's not working. They wanted something about time. So how do I use this to give them something about time? Which one of these labels up here is a unit of time? Seconds. So could we tell them how much it has in it? By doing that. As long as we tell them it's cubic millimeters, we'd say how many ever seconds you have, as long as we tell them T is for seconds, and that this is in cubic millimeters, we'll be okay. So we start with what we know, 4/3 pi r cubed. We say that's not going to work because they want this all in terms of time. And that needs to tell them how long the machine needs to run so that they can get this little balloon, you know, as big as it needs to be for the patient. So now we've got R of V down here. And C says, how could you use all this good stuff to write an equation that gives the radius as a function of time? That's what they want to know. How big does it need to get? And if you know how big it needs to get, how much time on the little machine before you hit end. In fact, they program that. They don't count on humans to be able to, you know, stop it at exactly 3 seconds. They program it into the machine. So R of V of T. That means we're going to take this little bugger right here. And wherever we see a V, we're going to put something we know about volume that has to do with time. So it'll be R equals cubed root of 3 something over 4 pi. We need to replace this something with information about time. 44t. And then we can simplify that, of course. You know, 4 goes into 44 11 times, so 3 times 11 would be 33. So the cubed root of 33t over pi. Now, hopefully they already have that equation, and it might actually be programmed into the machine. But what they want to know is, if they are putting that air into that balloon for 5 seconds, how big is that radius going to be? Well, we have the formula. All we have to do is throw 5 in here. And use a calculator. And we can tell them. Alrighty, so let's see. I need the cube root, which is under math. It's number 4. And then I want to tell it 33 times 5. And maybe I don't want to do any math in my noggin. So I'll just punch it all in. 3.745. Approximately 3.745 millimeters. And that's because we were taking a cubed root. Initially, you know, all of this would be in cubic millimeters because we were talking about volume, but when we take cubed root of something cubed would give us those millimeters. So, usually, this is stuff, unfortunately, that has to be done while the patient's on the table. And that's because they don't have any idea how big the plaque buildup is until they actually get in there. So, you know, there's a lot of training that goes on this machine to help people figure out this is how long it needs to run to give us this radius. It is not a guessing game. We need to know exactly where it goes. Now, some of you hopefully will be involved in the medical field, but all of you, I'm going to say, I hope, will go to college. And we have this, you're buying your first semester college textbooks. I don't even know if that'll be the case when you get there. It could be a lot of them are online now. You know, you pay a fee and you get the online book. Let me tell you, books have been out of control. Textbooks for the last few years from colleges, you're talking $300 or $400 for a textbook that you have to pay. So it would be really good if they have come up with an online form that's a little more reasonable for you. And the horrible thing about it is the professor chooses the book. So they might choose a book that nobody else in the school will use, and you won't even be able to resell it for a used book. So hopefully there's some good changes taking place in that. You're buying your first semester college textbooks. The bookstore is offering a special deal for this week only. You can use a coupon for $10 off your books and the in-store discount of 10% off your total purchase. And the best part, you can do a little math and you get to decide the order in which the discounts are taken. And does it matter? It absolutely does. It does matter. So P is going to equal the purchase price, and D of P is going to equal the final price using the 10% discount. T of P, the final price using the $10 coupon. So, D of P. You have a 10% off coupon, right? So if you're not paying 10%, how much are you paying? 90%, that's what you really care about. So we need 90% of P, because P is the purchase price. Well, T of P. That's the price of the book after the $10 coupon. You can think of that as just you go up and pay. They're going to ring up a price. You're going to hand them the coupon. They're going to take $10 off. So the question is, should you do this one first and then this one? Or should you do this one first and then this one? Is one of them a greater benefit? So let's check. Let's use composition of functions and let's figure it out. So what we want to do is D of T of P and T of D of P, and find which one's better D. So here's our D formula, and we have to put P minus 10 right in here, so that means we're going to multiply 0.90 times P minus 10. And that would give us 0.90 P minus 9. So far, so good. Now let's do it the opposite way. We're going to take this, and we're going to put it right there. Without actually putting a price in, can we tell which of these is the better deal? The second one, yeah. This one, you're going to do 90% of the cost, and then they're only going to take $9 off. This one, 90% of the cost, and then subtract 10. So what did they do first? They did the 10% discount first, and then did the coupon. So discount first, then coupon. So if you get to choose, that's the way you would want to go. The last piece we're going to talk about is implicitly defined things. This says write two equations for the final cost C if both these discounts are used in different orders, which is a better deal for you. So, this is kind of dorky, but C was D of T of P. And that's really what we're doing. I better make my C look bigger so this looks all official. Cost, D of T of P, equals 0.90 P minus 9. And then this one would be a great big C with T of D of P, which was 0.90 P minus 10. But I already talked through the second part of it. It's obvious which one is going to be the better deal for us. So just making it look official with their big C for final cost. All right, last topic of today is relations and implicitly defined functions. Implicitly means things that they're not, you can't look at it and see it. It's something that you have to kind of think through a little bit. So there are many curves in mathematics that do not pass the vertical line test and are therefore not functions. The equation for a circle, that's not going to pass the VLT. It isn't. But if we break it into two parts and say, I'm just going to graph the top of it, now it's a function. Or I'm just going to graph the bottom portion of it, now it's a function. So sometimes we have to do that, only use pieces of a function to get things to work. So however, there are often still useful geometric and or algebraic relationships between the points x and y on those graphs. The general term for a set of ordered pairs xy is a relation. A relation is anything that we can graph. If we just sat and came up with some random numbers and put them in ordered pairs, that would be a relation. Certainly doesn't guarantee it's a function, but it'd just be relations. So if the relation happens to relate a single value of y to each value of x, then we can call it a function. And its graph will pass the vertical line test. In the case of x squared plus y squared equals 4, hopefully you recognize that as a circle. Circles have perfect square plus perfect square equals a perfect square over there. Both 0, 2 and 0, negative 2 are in the relation. So as it sits, that's not a function. Now, how would we know that? Algebraically, we would know it by solving for y. That's what we would do. We'd say, hey, I've got to get the x squared over to the other side. Or you could write it as 4 minus x squared. It won't matter. But when I do this, and I'm trying to get y by itself, I realize, uh-oh. I'm going to have a problem. Now I could just deal with the top portion of the circle. That would be the top portion because that would be the positive portion of that circle. Or I could deal with just the bottom one. And by giving that restriction, I would have a function that I could use. So sometimes just because something's not a function, it doesn't mean that we just totally give up. We can split it up and use those implicit definitions of the function to move forward. All right, so let's see what they're going to give us about these. Determine which of the ordered pairs are in the relation defined by x squared y plus y squared equals 5. And finally, is the relation a function? Can you tell by just looking at it whether or not that's a function? Is it or isn't it? Not going to happen. Why? Y squared. Yeah, we can answer this right away. This is a big no. But they want us to see a little deeper than that. They're saying, you know what, go ahead and try these numbers in here. So 2, negative 5, 1, 3, and 2, 1. And see what happens. So if we put 2 in for x and negative 5 in for y, we want to see whether or not that makes this true. Well, order of operations, we'd have 4 times negative 5, which would be negative 20. Negative 5 squared, 25. Yeah, that's 5. That one works. That one's a yes. One, 3. See if it works. 1 squared times 3 plus 3 squared equals 5. Well, 1 squared is 1. 1 times 3 is 3, and 3 squared is 9. Uh-oh, that's not going to happen. This one is a no. It's not on there. 2, 1. 2 squared times 1 plus 1 squared equals 5. Well, 2 squared is 4. 4 times 1 is 4. 1 squared is 1. Hey, this one's good. What do we have as secondary proof that this is not a function? Put a 2 in, you get a negative 5, and you also get a 1. 2 outputs, which we knew was going to happen anyway because we saw the y squared up there. So now this one says, let's consider our circle, which I actually already did on the last page. So we had y equals plus or minus the square root of negative x squared plus 25. Except in the other one, I think it was a 4, wasn't it? Okay. But I don't think we need to go all the way through that. So we have that. And they're asking, what would the graph of each of those look like? I mean, if you just separated this and said y equals the square root of negative x squared plus 25, and y equals negative square root of negative x squared plus 25, what would you get? Well, you have to know what the relevance of the 25 is. In the circle, x squared plus y squared equals 25. What's the 25 for? We've forgotten our circle formula. the radius squared. So that means our radius is 5, which means from the center at 0, 0, since there's nothing along with these x squareds and y squareds, the center is at 0, 0. We need to go 5 out in every direction. So if this is the positive portion, I'd go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. What I'd be off 1, 2, 3, 4, 5. Those are teeny. And then just do the best I could to draw a semicircle, you know. And I know that's not going to be perfect. So what's the negative one going to do? Where's it going? This was our positive. Where's our negative? We're all drawing it, but nobody's talking. Where do you get it? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Do the best you can to get a semicircle. Do you see how each of these alone is a function? It would pass the vertical line test, it would. But together, not a function. Not going. So we can implicitly define these. Now, this next problem is just super cool. Since all the ordered pairs in either of these functions satisfy the equations x squared plus y squared equals 25, we say that the relation given by the equation defines the two functions implicitly. So if we put those two together, we'll get the circle. But for certain things that we need to do in calculus, it just isn't going to happen if you're not working with functions. So you'd have to split it apart. So this one, look at that bugger, huh? Ooh, that looks like fun. What we want to do is see what this is when it's implicitly defined. So that means we have to get y by itself. Big hint on this one. Factor and solve for y to find the two implicitly defined functions. So look at this and I think, wait a minute. I think this is a pattern I'm supposed to know over here. This is a perfect square and this is a perfect square. So x times y times 2, hey, that's a perfect square binomial. So it's like completing the square. And then we think, okay, if I'm going to gain access to that y, I've got to get rid of that squared thing. Uh-oh. There's our two outputs. And to get y by itself, we would have to subtract x. So now we separate these two. And we realize it's going to be y equals negative x plus 1 and y equals negative x minus 1. What's that going to look like when we graph it? It's two parallel lines. This is an equation for two parallel lines. Isn't that awesome? Look at that little bugger there. Equation for two parallel lines. So if we graph it, we can do y equals mx plus b, and we can say this one's going to start at positive 1, slope is negative 1, so down 1 and right 1. Graph that as a line. Then go after the second one, which starts at negative 1, but has the exact same slope. One equation that gives two parallel lines. That is cool. That is cool. So we solve for y and we see the two different pieces that we have there. So today we had a lot of objectives. We talked about composition, we talked about decomposition. We talked about modeling, which basically meant word problems with composition, and then we had our implicitly defined stuff. So 43210 me, how do you feel about the week of the day? The word problem's the toughest part? Okay. And that's, yeah, with practice, it'll come. So practice we will do. And when I did this assignment last night, I remember thinking the problems on here are not as difficult as the things we went over in the notes. Well, that's right. There weren't really any good word problems in this. Yeah, we couldn't find anybody that anything that matched with what we had talked about. So don't be afraid of the assignment.